Hello everyone. In this session, I am going to give you people a complete idea of the stack organization within the computer system. The registers within a computer system can be organized in three different ways. Being a designer, you can choose one of those organizations. That is, the first one is single accumulator organization, second one is general register organization, and the third one is the stack organization. When it comes to the single accumulator organization, we do have only one general purpose register, that is accumulator. When it comes to the general register organization, in addition to the special purpose registers that we do have in the single accumulator organization, we are provided with a few general purpose registers to support our special purpose registers. In the general purpose registers, we will be able to store any kind of a data in order to speed up the computation. Now let us understand what is stack organization. You might have heard about the stack already in your first year of engineering. And you know how important is stack because every now and then you used to use this stack in your programming. But why the stack is considered to be one of the best data structures for a program? When you ask a programmer which is the best data structure, obviously a programmer or a designer is going to give you only one answer, that is the stack. Stack is considered to be the best data structure for any programmer. Let us understand why. In the initial days of computing, this program execution was proven to be a headache. If you are a programmer, the problem is you should be able to accommodate the return address when a function calls another function. Let us see what it is. Consider that you are a programmer in 1960s. You have written a program in some programming language. There are several functions in your program. These are some of those functions within your program. F1, F2, F3, F4. Now let us say F1 calls F2. When F1 calls F2, F2 becomes the subroutine, F1 becomes the calling routine. This is the calling routine and this is subroutine, can also be called as called routine. Now, when F1 calls F2, F1's return address must be saved somewhere because the moment F2 gets executed, F2 should make a return back to F1. For that, we should be able to store the return address of F1. Let us see what it is. Let us have a look at how F1 is going to make a call to F2. And the program gets loaded in the main memory. Let us say the F1 is calling F2. That is, at a specific address within the F1, there is a call instruction. Call to 430. Right from 430, let us see the F2 is originated. F2 is available from 430 to 440. Now, when a call instruction has been made, immediately the program's control will get transferred to the first instruction of the subroutine, that is 430th instruction, which is available at the address of 430. But let us understand, I can't blindly go to 430. Initially, I should be able to save my return address. What is the return address? Return address is the next instruction's address because we are suspending one routine here. Now, the moment the call routine is executed, the calling routine should be resumed. For that reason, our program counter value, which is the next instruction's address which has been suspended, should be saved somewhere. Now, here the problem for a programmer is accommodating this program counter's value, showing a provision to store the program counter's value when a function calls another function. Initially, during the initial days of a computing, this provision was memory of 0. That is, if you want to save the program counter value, being a programmer, you are provided with a provision that is M of 0. What is M of 0? M of 0 is just nothing but the first location within the main memory. The moment one function calls another function, the current function's return address, that is the program counter value, will get saved automatically in m of 0. That is, when this f1 calls f2, before I go to 430th instruction, which is the first instruction of f2, I need to store this 24 in m of 0. Since m of 0, that is the first address within the main memory, is the only provision for storing the return address when a function calls another function. So now I am storing 24 before I call 430th instruction, which is the first instruction or the origin instruction for f. Now, the moment the final instruction gets executed in f2, a return should be made to the 24th instruction. Now, at the end of this routine, there will be another instruction which takes you to m of 0, that is jump to 0. What is jump to 0? This jump instruction takes you to the address in which it is being supported with. Jump 0 stands for a jump will be performed to the address 0. Now it is quite evident that at the end of each and every routine, we are going to find out this instruction. That is purely because when f1 calls f2, f2 becomes a subroutine for f1. At the same time, f2 calls f1, f1 becomes f2 subroutine. So it is quite evident that at the end of each and every routine, we should perform a jump to 0 because all the return addresses are saved in memory of 0. Okay, now in this case, things are pretty simple. f1 calls f2, f1's return address is saved at 24. Now the moment f2 gets finished, I need to perform a jump, which is obviously done by jump instruction, to 0th address. Then a jump will be performed. This is an unconditional jump. After which, in 0, 24, the address 24 will be collected, taking this address, going to this specific instruction. The previous calling function will be resumed. The calling function will automatically be suspended when a subroutine gets called. That program counter value will automatically get saved in memory of 0 initially during the initial computing days in 1960s. But the problem here is, for a programmer, what if this f2 performs one more function call? Here you can clearly see f2's return address must be saved. f1 calls f2, fine. But what if f2 calls f3? Here you can clearly understand. From f2 to f3, function can never be called. This is simply because we do have only one provision to store only one return address. But in this case, when f2 calls f3, this f2's return address must be saved, which obviously is going to override the previous return address, that is 24, right? This is the reason why, by using the single conventional memory of 0, only one function is allowed to call another function, and the called function should be strictly returned back to the calling function. The called function cannot perform one more call to another function. That means that nested subroutine calls are not possible, because memory of 0 is only one single convention in which only one return address can be saved. Multiple return addresses can never be saved in memory of 0. So it is f1, it is f2. When f1 calls f2, f1's return address has been saved. What if f2 calls f3? Let us say f2's return address is 435. Where are you going to store this? If you decide to make a call from f2 to f3, then this 435 must be saved. At that time, this 435 is going to overwrite 24. This is the reason why it is strictly prohibited. Nested subroutine calls are strictly prohibited. But a program is all about nested subroutine calls. Being a programmer, you know how vital and important to implement this nested subroutine calls within a program. Otherwise, the modularity doesn't work at all. The speed up will get reduced. So, but in the initial days, as there are No other choices. Only memory of 0 was used to be a convention in which only one function can make a call to another function. After which, to the called function, there must be a return back. That's it. Now, what are the alternatives? After which, the designers invented one more approach to store the subroutine value in which multiple subroutine calls are allowed. Let us see how that is going to happen. The next convention, rather, the next provision is to store the program counter value is origin of subroutine. What is origin of subroutine? Let us understand. Let us say this is F1. F1 is from 20 to 30. This is F2. F2 is from 200 to 240. This is F3. F3 is from 400 to 450. Here, as I'm going to use the origin of the subroutine provision to store the program counter value, what is exactly going to happen? Let us have a look at. Now, when the program is getting executed, let us say the function 1 of the program is getting executed. Now, let us say in 23, there is a call instruction. Call to 200. This is F2. Immediately, the moment the call instruction is executed, the control will get transferred to the first instruction of F2. But before that, you know that the program counter value must be saved, which is 24. In the initial days, we used to store this program counter value in M of 0. But M of 0 provision has a serious drawback. That is, it can allow only one program counter value, but not multiple program counters value. So what we do is, we are using the convention to store this program counter value in the initial address, the starting address of the subroutine itself. So when a call has been made, this program counter value will be collected and will be stored within the first address of the subroutine, the origin of the subroutine itself. So within 200, in this initial address, in the initial location, the previous program counter value will be saved. Okay, and right from 201, actual subroutine will get started. Finally, as the subroutine gets finished, there will be a jump performed to the initial address, the starting address of this subroutine, jump to 200, in which you will be able to jump to the initial address. In the initial address of the subroutine, the previous program counter value has been saved, collecting which you will be able to return back to the previous routine, which was suspended, which was considered to be the calling routine. Here, nested subroutine calls are absolutely possible. Now here, let us say this subroutine is calling another subroutine, that is F3. Now in 202, let us say there is another call instruction to 400. Now this 203, which is the program counter value, as it has to be saved, collecting this program counter value, going to F3, we should be able to save this 203 in the initial address. That is, in 400, we are going to store 203. Finally, the moment F3 gets finished, there has to be a jump statement which jumps to the starting address of the subroutine, that is 400. So again, a jump will be performed. In the initial address, the previous program counter value has been saved, collecting which we will be able to return back to the previous routine which was suspended. Then we will resume the previous routine which was suspended, after which we are going to take another jump to the initial address, in which the actual subroutine from where all these nested subroutine calls has been initiated, the program counter value is available, taking which we will be able to return back to the first subroutine which actually initiated this series of the subroutine calls. Now, here you can understand nested subroutine calls are absolutely possible because we are using the convention. Here, these are multiple conventions. I'm not using a single convention. So first, Let us recollect what happened. F1 calls F2. Now, when F1 calls F2, control will be transferred to F2, but there is a slightest change from the previous case in which the program counter value will be initially saved in the origin address of the F2, after which the actual subroutine will get started. So obviously, there is no need to tell you that the starting address of every routine will be empty. It is going to accommodate the program counter's value. And the ending address of every routine will be a jump statement to the starting address. So it is needless to say, because a program is a collection of functions. Any function can call any function. Now here the sequence of function calls is F1 to F2, F2 to F3. But after some time, F2 may call F3 and F3 may call F1. Now anyhow, a function can be called anytime by another function. At that time, this function should be able to provide a provision for storing the previous function's program counter value. For that, every function's initial address must be free. This initial address will accommodate the program counter value of the calling function. The final address is a jump statement to the initial address. So here the thing is only F1 to F2, F2 to F3 has been called. So F1 24, which is the program counter value, will be saved in the F2's initial address. The moment F2 gets finished, a jump will again be performed to 24, rather, the initial address in which it will get collected. What if F2 calls F3? Simple. F2's program counter value will be saved in the initial address, that is 400. After storing the program counter value in the initial address of F3, then actual subroutine will get started, and also the final address is just nothing but a pointer to the initial address. Okay, so we're going to make a jump to the initial address in which the previous program counter value has been saved, taking which we are going to finish, after which taking which we are going to branch to the first location in which the previous program counter value has been saved. So finally F1 will be returned, then F1 will get finished. Here fine, nested subroutine calls are absolutely possible, but something is still not possible. What is it? Here the thing is, recursion cannot be possible. There is no provision for recursion. What is recursion? The function calls itself. Of course, this feature absolutely doesn't work. It is quite evident from the discussion that the recursion can never be possible. What if F3 calls itself? F1 calls F2, F2 calls F3, but what if F3 calls itself? Let us say in 425, there is a call to 400. That is, this function calls itself. At that time, 426 must be saved. This 426 is going to be saved as in the initial address of the subroutine. Unfortunately, in the initial address, we do have the program counter value of the previous routine from where this routine has been called. So obviously, this program counter value will be overwritten when the recursive function is going to get executed. So in this case, the recursion is absolutely not possible at all. So from memory of 0 to origin of subroutine, there is some advantage in which nested subroutine calls are possible. But the problem is in which in the origin of subroutine case, recursive functions are not possible. So what we do is we use a stack to store the program counter's value, the return addresses when a function calls another function. Let us see how efficient is a stack when it comes to storing the return addresses. You know that the stack is a linear data structure in which the item which is pushed last is going to be retrieved first, right? Now let us say there are three functions, F1, F2, and F3. Every time when a function calls another function, the function's return address will be pushed into the stack. Let us say at 23, there is a call instruction to 400. 24 will be initially pushed into the stack. Let us say it is in between 400 to 450. At 425, there is a call to 600. So 426, which is the return address, will again be pushed into the stack. That is 426. After which, the third function, which is originated at 600, will get started. Let us say this F3 calls itself. That is a recursive function. Now, let us say at 649, a call to 600 has been made. So that is 650, which is the program counter value, will be pushed onto the top of the stack. Okay. So it is quite and clearly evident that a stack is going to support all kinds of returns. That is, all the program counters values, including when a function calls itself, will get pushed into the stack. As the stack is a LIFO data structure, obviously the function returns will be appropriately and exactly will get performed. Let us say this is executed, after which 650 will be retrieved. Then from 650 to 700 will be finished. After which, again a pop operation will get performed. In this pop operation, 426 will be popped up. Then F2 will get executed. The moment 450 gets finished, F2 is finished. So there will have to be a return back to F1. Again, a pop will be performed, in which the initial address that has been pushed into the stack will be retrieved, taking which we'll be able to resume F1. This is how the stack is going to support all the cases of subroutine calls and returns. In M of 0, only one function can call another function. In origin of subroutines case, recursion is not possible, although nested subroutine calls are possible. But when it comes to the stack, without any ambiguity at all, we will be able to implement all kinds of subroutine calls and returns. This is considered to be the excellent data structure in which there is no memory wastage at all. And the things are proven to be very fast indeed. This is the reason why the programmer's best choice data structure is stack all the time. In the next session, we're going to have a look at the different kinds of stacks within a computer system. Thank you.